Welcome, everybody. You are in Ballroom A, the best ballroom. You are here to see geospatial validations using FastAPI and PostGIS. I'd like to give it up for Lazouich Ford.
Thank you for joining me on this talk today. I'm Lazouich Ford. I'm a software engineer. My day-to-day, I'm mostly working with wildfires, so I'm not a stranger to geospatial data. The accompanying repo is on my GitHub there. So hopefully by the end of this talk, you'll have a high-level understanding of what geospatial data is. I also hope you have like a broad sense of how to use PostGIS to query geospatial data, and then ultimately, probably while you're here, how to actually use it with FastAPI. So let's start off with geospatial data and like explain it like I'm 5 exploration of this data. So geospatial data you've probably run into before, whether or not you realized it. Something as simple as like Apple or Google Maps, that's going to be geospatial data. If you ever look at like a map of train stations trying to figure out where you're going, that's geospatial data. Or in this picture here, I actually have what is a shake map of a earthquake from 2010. This, is probably what you'll run into when you run into geospatial data on something like the news, following some type of natural disaster. The typical geometries that you'll run into when dealing with geospatial data, usually going to be a point, a line string, or a polygon. You can also have a collection of those, so you might have something like a multi-polygon or a multi-point. Now, I do want to give everyone a warning here that this next slide might trigger some of you. So the Earth is not flat, and there's no simple way of putting it down on a flat paper map or computer screen. That comes straight from the PostGIS documentation. And why do we care about that? Well, when we go and we use geospatial data and we have something like the globe, which is a spheroid, when we try to project that to something flat, we have to choose what are we willing to give up to do that? What kind of distortions are we willing to take? And there's different trade-offs for that. That would take too long to go through with probably 3 hours of your time. So I will let you explore that link to see different projection types and the trade-offs that you would run into for using each one. But ultimately, the reason I bring this up is because if I were to ask everyone in here to stand up and take 5 steps to the left, would you all end up in the same position? No, right? Because you all are starting in different positions. Everyone has different step sizes. And then some of you aren't going to move at all because you're going to say, is he talking about my left or his left? So we have to have some type of common ground of what we're talking about when we're saying, hey, I have a point that's located here. And these are known as spatial reference systems. So all it's doing is describing where on the Earth geometry is. One that you probably use most often, especially in the US, is going to be the World Geodetic System from 1984. This is what's used by GPS. You can assume everything that I'm giving you is going to be in this reference system. So with geospatial data, you can encounter it in many different formats out there. You have shape files, you can have it in a CSV. My favorite is just going to be a .SQL file, and that's because I just load it into a database and I don't want to have to do anything else with it. But the most common type really that you're probably going to find is a shape file. A shape file is a little bit of a misnomer. Shape files are made up of multiple files, as you can see in the picture here of a directory of if you were to open up a shapefile in your directory. And so it's worth noting that, it's probably what you're going to run into. And if you download one and you're like, oh my gosh, there's so many files in here, I must have done something wrong, you didn't. We're going to move on to PostGIS. PostGIS is an extension for Postgres. It allows you to work with geospatial data inside of Postgres. So to install it, I'm going to assume that you already have Postgres installed on your machine. It's really simple. Just create extension. I like to use if not exists, PostGIS. If you have some type of specialty need for installing it, the actual PostGIS website has plenty of instructions on there to help you through. But since I did mention to you that shapefiles are what you're probably going to run into, I think it's only fair that I tell you how to load those files. So the shape2 PGSQL comes a part of when you install PostGIS. You can run it right from your terminal, and it's just going to convert your shapefile into an SQL file. So the generic form of that is going to be on the box at the top there. Really simple. Shape to PGSQL, whatever options you're putting, the shapefile that you want to use, the table that you want to load that data into, and then the out file that you want to shove all that data into. So in that black box there, if we assume that that's actually a terminal running, we have this shape to PGSQL, that .cdi, which is just telling it, hey, I want you to create me a new table, use Postgres dump format, and probably most importantly, make that geometry column, I want to use that as an index. And then that .s is what we use to specify our spatial reference system. And we give it the shapefile there, and then we're saying, hey, in my public schema, I want to put that into my US boundary table, and finally, give me that all back in a .sql file that is called US boundary. So the common functions that you probably run into with PostGIS are these ones. I do want you to kind of notice that asterisk on sttransform, because I'm going to tell you how to do it, how to use it, but I don't actually use it. And the only reason I'm telling you what it does is because otherwise I get a bunch of angry emails about how you spent all this time hitting your head against the wall because your data that you're using and the data you downloaded were in two different reference systems. So first we have this stMakePoint. Anyone have any type of guess of what MakePoint does? If you thought MakePoint, good job. 500 points for you. So if we were to plot something like this, we get just a point. Look at that, a point roughly where we are here in Pittsburgh. Wonderful. But this stMakePoint, you usually don't use it on its own because of that spatial reference system. So you're almost always going to use it in combination with this stSetSRID. Any idea what this setSRID does? If you guess sets an SRID, you would be right. You now have 1,000 points total. And if you were to actually use this in a query, it would look something like this. We can just do select, stMakePoint, and then longitude, latitude. Do notice it's longitude, latitude. That is not a mistake. It really is longitude, latitude. I know you're probably used to hearing lat long or latitude, longitude. I promise you this is correct. And then, of course, as I just mentioned, you're probably going to want to use this with set SRID. So that's what we do here. We have the set SRID with the geometry and then the SRID that we want to specify. And to actually make that point that I just had on a few slides ago, this is what that query would look like. Next, we'll move on to st_intersects. This is going to return true if two geometries have any point in common. Visually, that looks something like this. You notice we have a point in the same location, and then I have this blue polygon. Since that point is inside of that blue polygon, this would return true. The query for that is going to look something like this. Simple again, st_intersects geom1, geom2. I probably should mention that you won't use it in this form as much. You're probably going to use it in something like this, where you're saying, hey, give me all the rows from this table 1 where the geometries from the rows in table 1 intersect with whatever my geometry of interest is. Now let's talk about this ST contains. It kind of seems like it would be a lot like ST intersects, which a little bit, but it returns true if and only if all of the points of geometry B are inside a boundary of geometry A. So if we look at this orange outline of Pennsylvania, you see that the blue triangle inside of that is completely inside of it, so that would return true that the orange boundary does contain that blue triangle, whereas that red polygon there has points outside of it, so that would return false. Now we have ST distance. Any guess of what ST distance does? Okay, 1,500 points total. So for geographies, this is going to be the minimum geodesic distance between two geographies in meters. So you would probably think that the line that you're measuring the distance along, it looks something like this. If you did, I'm sorry, I have to subtract 500 points because the Earth isn't flat. So while I am really exaggerating it here, the real distance that you're measuring is going to have a little bit of a curvature to it. It's going to look something more like this. But it is important to notice that it isn't just straight. You know, even though we look at these things on a flat screen or a flat piece of paper, the physical objects that they represent are not flat. And then finally, this ST transforms that I mentioned earlier, and this is just going to give you a new geometry with the coordinate system that you specify, so it's how you can go from one coordinate system to another and not have these problems of not being able to get the distance or an intersection to work because you have data in different reference systems. So probably the most interesting part here is how we actually use this with FastAPI. We want to look at why we would want to even validate geospatial data to begin with, and it's really why you would want to validate any other incoming data into your system. Known bad requests fail faster. If you had the money and you won an auction for a decommissioned supercomputer, you might not want to spend the money on the energy costs to keep running processes that are going to fail. And you can protect that with actually validating the data that you're putting into your system. Or, maybe something that you'll actually deal with in a day-to-day is when it comes to computational costs. So if you have a system and inside of your system you have a synchronous call that no matter what is going to be 5 seconds to get that response. You don't want to run that just to have it fail because you put bad data into your system or you got bad data coming into your system. We want to protect our systems from dealing with bad data. It also allows your code to be concise. It can deal with the business logic or the actual problem that it's solving. You don't have to worry about weird edge cases that you're worried about from random data coming in or anything like that. When it comes to actual geospatial data, the type of validations you might want to use is something like, hey, is this point inside of a boundary? Is this point a certain distance from another point? Things like this. So the general overview of this project, these are the assumptions you can make. It's a FastAPI app that I have an endpoint that it validates the data using Pydantic. I also have an endpoint that validates the data using dependency injection. And then I have a database table that's loaded with the geometry of the boundary of Pennsylvania, and then another one that has a bunch of geometries of different neighborhoods in Pittsburgh. So if we go and we can put this all together where we have what we did with PostGIS, and we want to put that inside of a Python function, it would look something like this if we use SQLAlchemy. This probably doesn't look too surprising for you, but let's go over just that SQL portion of it. So here we're asking for the ID from this Pennsylvania boundary table where the geometry intersects our incoming point. I'll let you know right now that this table only has one row, so if we get any type of response, we know that that point is inside of Pennsylvania. I don't want to hear in the hallways like, the earth is flat. I also don't want to hear, you used raw SQL inside of Python, I'm so mad at you. I'm going to show you how to do it using an ORM. Everyone will be happy. So on the left, we have the SQL. On the right, we're going to be using SQLAlchemy. If we start here with just that select portion of it, if we were to translate that using the ORM, we just have this session.query, PA-boundary.gid, which is just, that PA boundary is just going to be a table model there. If we move on to that where portion of our query, to translate that portion, we just have this dot filter. And then something really nice here is that we have almost the exact same thing, right? The intersects, the SRID, the make point, and then basically the geometry as well. The only difference being that we access that again through our table model. So if we were to replace what some of you guys would think is, just so bad with having that text portion in there, with now this ORM, we have a function that looks something like this. And you might have been wondering, like, how did you use those PostGIS functions right in there? Well, luckily for us, there is a library called GeoAlchemy 2, which allows us to import those directly and use them directly, which makes going back and forth very, very simple. And then finally, we're going to look at using these geospatial queries with endpoint dependencies and then Pydantic model validations. So if in our main.py, which is just a very simple FastAPI app, we have something like this with a post endpoint here. You'll see here inside of this post, we have this dependency depends point intersection PA. If we actually look at that function, you see that we take in a point, which is just going to be a very simple Pydantic model with a latitude, longitude, and we tell it, hey, this is coming from the body of our endpoint there. And then that if not point intersects Pennsylvania, that's going to be the same check that we just went over a few slides ago. And so if we get something falsy from this, we know that the point that we're trying to bring into our system does not intersect Pennsylvania. We want to reject it, so we raise a 422. If none of that fails, then we can go ahead and what we'll do is we'll return the neighborhood, if it exists, that that point resides in there. If we look at doing the same type of thing using a Pydantic validator, we can see our endpoint looks something like this. Notice that that inside of that app.post, we no longer are specifying any type of dependency. Instead, what we have here is this point with validation. So this point with validation is going to be a Pydantic model that we have here. If we look at the first portion of it, we're just taking in a latitude, longitude. I specify some defaults to make my demo a little simpler. But other than that, nothing funky going on. If we move on, though, down to this model validator, you notice that it's basically the same as the endpoint dependency function that we specified. We check again if that point intersects Pennsylvania. But notice that instead of raising straight 422, we actually raise a value error, and that's just because, luckily for us, Pydantic will take care of that for us and return the 422 on our behalf. So if that validation runs into no issues, what this endpoint is going to do is just going to echo back out your point to you. I do want you to notice, though, that I have this response model that I specify in the app.post. And this response model is that point with validation again. So what that is going to do for us is that if for some reason the outgoing data doesn't check pass that validation, it's going to raise an error as well. So let's look at this in action. You see that all right? Okay. So all this is the docs portion that's given to you for free from FastAPI, one of the nice things about it. If we go and try out this endpoint here, I have this point, which I'm going to let you know right now, is located inside of Pennsylvania. If I go ahead and hit this endpoint, you notice that it just echoes back our point, right? Our latitude, longitude, nothing special there. But if I go and I change this, and let's just remove that 8. So this point's no longer inside of Pennsylvania. If I hit this endpoint, we get that value error, right? We get the 422, the value error, and it lets us know that the lat long must be located inside of Pennsylvania. So it works just as expected. I added an extra endpoint here that no matter what I put inside of it, it's always going to try to return a latitude and longitude of 0, 0. So even though this is the same point which we know is located inside of Pennsylvania, and it will pass that incoming validation, if we try to execute it, we get an error. And that's because of that response model that we specified when I said that the outgoing data has to pass that same validation. So that's one of the nice things of using a Pydantic model for your validation, is that you can validate the outgoing data as well. And then if we move on to where we did the endpoint dependency, this point, I'll again let you know it's located inside of Pennsylvania. If we run this, we see that the neighborhood that this point resides in is the central business district. That point is basically where we're located right now, so now you know we are inside of the central business district. If again I change this to a point that's no longer inside of Pennsylvania, we run it again, bam, 422. You don't get the value error because we're not using the Pydantic validator, but we still throw a 422 all the same. And then that is all I have for you. So I thank you. The accompanying repo is on my GitHub there. If you have questions or want to connect with me, my LinkedIn is there as well. And we actually have a good bit of time for questions. So if you have some questions, I know there's mics on each side. Yeah, you just have to line up at the mic so they can get it in the recording.
Hello, thank you for the talk. I'm curious, just generally best practices that you've seen for managing SRIDs and transforms of data. If I were to be ingesting, say, a whole bunch of this data into PostGIS.
So you'll find a lot of the times that if you're working with a single data source, that they're going to give you the data in the same reference system. I'll make sure that I put that link from one of the first slides going over different projections and the pros and cons of them inside of the README of the repo. But it's really going to come down to what you're trying to do, because certain projections will preserve different things. Some might preserve distance, some might preserve area. So it really comes down to what you're actually doing with the data.
I'm not sure exactly how related it is, but one of the problems that I've run into quite often is we get data coming in that's in a site local thing, so it's just it's this many feet from the bottom left corner of the facility. How difficult is to set up custom SRIDs that then you could translate back and forth between something like that?
I'm going to be honest with you. I don't have a good answer for that question. It's definitely goes to one of the difficulties of working with like very local SRIDs. And especially if you're dealing with like, this is 5 feet from the left, from this point. It's not something that I encounter on the daily, but I'm sure someone else has like solved this problem and will grab you and be like, this is how you solve it.
Yeah, thank you. That's exactly what I was hoping for, is that someone would be like, oh, it's really easy, just do this. So, good to know it's not actually easy and we're just missing something. So, thank you.
I'm also curious how far you've pushed managing raster data with PostGIS and any strengths and weaknesses you've seen.
So I've used raster data with PostGIS a little bit in terms of like, I have one data set that I have to use with it. So I guess like to directly answer your question, I haven't pushed it. I've really just done like, hey, this location, give me the value, kind of what you would expect with raster data. Yeah.
Totally off the wall question. What slide program are you using?
Just Keynote. Yeah, comes standard with most Apple devices.
Hi, one question. At the start of your presentation, you showed that you don't use shape files, but instead you use the SQL directly because of like shape files has many different files that actually contain it. Can you explain like what's the actual difference between them two? Because like I once tried to use shape files, and I think I only had one of them, the SHP instead of SHX, and it didn't work. So why, like, or in other words, is the conversion from SQL, or from all these 5 different types of shape files to SQL is like 1-to-1, or we kind of losing some resolution or some information? What's the trick there? What's the difference?
So I don't want to 100% say it's 1-to-1 because there is a lot of data that you can get inside of a shape file. But if you only have the .shp file, the reason that it's not working for you is because each one of those files contains different portions of the data. So some of it contains just the geometry data, some of it contains like SRID data, and then the actual like table data that would be just all the other data that's not the actual geometry data. That's why, I can't remember off the top of my head, but I think there's like 3 of those files that you have to have when using a shapefile. So the conversions, though, you shouldn't really run into an issue with data loss as long as you have like a complete shapefile to begin with.
All right, so SQL basically turns all 5 into 1.
Yeah, that shape to PGSQL, that's what that's doing for you, and then just giving it to you in a format that is, the .SQL file is really just going to be like an insert into this table and then all your different columns like you would normally do with an insert statement.
All right, cool, thanks. Good presentation, by the way.
Thank you. Any others?
All right, I think it's break time. Thank you, Lazouich.
Thank you.